Okay, hello everyone. This is Tom Ballard, the Groundwater Guy, with another edition of Groundwater Talk Live. And today we're talking about designing wells for the long haul, and that's kind of my semi-catchy title there. But what do we really mean? We talk about wells where we're designing wells, and we're talking a lot about we're getting our geophysical logs, we're putting our screen intervals where we're supposed to, and all that type of thing. There's a lot of design considerations that we talk about endlessly. But the one thing we don't talk about a lot is designing wells for maintenance, rehabilitation, and repair. And that's something that really gets short shrift here. And that's really what I'm talking about, designing wells for the long haul. It's something that we really need to look at. And as I look at a lot of wells out there, and we run into problems as wells age, it's really not something that ends up being a design consideration, and it really should be. So we're going to talk about this a little bit today. It's really more of a discussion type of thing. And really like to get comments from people. I may say some things that are a little bit controversial. I know there's one here that probably goes against the grain a little bit. One of my points here, but I'd like to get comments from folks on this. So if you're watching, if you can drop a comment in the chat as we go along, and later if you're watching the recording, like, share, comment. All that stuff is helpful getting the word out, as well as I like to get your feedback on stuff like this. So it's a lot of our experience, drives what we do, and other people have different experiences, and so it's really helpful to talk to people with different sets of experience because we can learn from that. All right, so let's dive in a little bit here. So really what we're talking about is traditionally wells were designed for 25-year life, and that's kind of the asset class that I think the EPA still looks at when you're doing asset management. They look at wells as a 25-year life, and that's how they were designed. But really when it comes down to it, um, for a lot of reasons, current wells that we're looking at, we're really going to try to squeeze 50 to 70 years or more of life out of these things. They're expensive. Um, the materials have gotten a lot better over time too, so we can expect that. But if you're going to run a well that long, we really need to look at the practical considerations of how do we maintain that well. You're not just going to plunk a well down in the ground and run it until it stops. You're going to have to do some maintenance like you would on a car, changing the oil in your car. Same thing with a well. There's going to be some maintenance. You're going to have to pull the pump, fix that. You're going to have to do some well rehab over time, and those consider with the 25-year life. Sometimes you can get away without really doing much of that, but with wells that are lasting for going on 100 years now, it's really a consideration that we really got to look at. How do we maintain these things? Because we want them operating at their optimal conditions for what they are, for their entire lifespan. So if you have a well that's 50 years old, we still want it to be pumping water and getting most of the capacity that it originally had. And that's going to require some kind of maintenance. And that's what we're talking about here. There's a lot of reasons why we're looking at the longer lifespan on wells now, but going back to our traditional look-see here, typically the way most people approach wells is what is going to be the lowest cost to meet the minimum standards that the state requires. In California, you have your California well standards by the Department of Water Resources. Most states have a set of requirements. We also look at things like the American Water Works Association A100 standard, which they keep up to date, unlike the California standard here that's well out of date, and they keep saying they're going to update it, but it's still a work in progress, I guess. But so we're looking at, and we go out and we put together our specifications, and we go out and we get the low bidder, and our specifications are usually based on on the state well standards or something like the AWWAA 100 standard. And that's really what we're designing for, is the minimum standards. Now, I know these standards like the back of my hand. I look at them all the time, and they really do not take into account the considerations that we're talking about here today, is designing for well rehabilitation and maintenance. And some of these things go against the grain a little bit, and that's kind of where I'm looking for comments from folks too, and make it more of a discussion type of thing. So that's really kind of the approach that still gets taken, as if we were looking at a 25-year well life, when we're really trying to squeeze out 3 or 4 times that. So is really what we're getting down to at this point. All right. And there's also more. There's always more, of course, but especially in California, we have the fallout that we're seeing from the governor's executive order N-7-22, which had Section 9 in there, which really basically put the crimp on permits for new agricultural wells that required you to jump through a lot of hoops that made permitting a lot more difficult and expensive, and really has cut back on the permitting there. Now, a lot of counties, and we've talked about this in several episodes here, a lot of counties out there have taken that farther than just agricultural wells, and they're basically suspending permits for any new wells, including municipal wells, unless you can meet certain standards as far as documenting interference and subsidence, according to the governor's orders, clearance with the Groundwater Sustainability Agency for that particular basin. This usually means a hydrogeologist report, and really adds to the expense of the permitting. So what we're going to see, and this is something we've seen coming for a while, is that we're going to see a lot more restrictions on new well permits. So when you do put in a new well, you want to design the well, probably want to go beyond the minimum, because you're going to be asking, yeah, Ned, thank you. That's a huge part of the problem, and that's kind of the point here. And so I'm glad Ned is on, because he really knows the problem here. So I'm talking about California. We're looking at probably a lot of restrictions. So your wells are really a valuable asset, and you're going to need to protect those assets, and maintaining that asset is an important part of that. So maintenance and rehabilitation are required to maximize the lifespan. I'm really surprised at how often I get out there and see people that have wells that are 25, 30 years old, and they've never even done well rehabilitation. And so that just needs to be something that you build into the process, and it's really a matter of education. So you're going to have to, in order to maximize the lifespan and keep that well operating in tip-top condition, you're really going to need to do the maintenance and the rehabilitation. Most wells not designed to facilitate that. So and so we're going to talk about some of those components here. So we really need to design our wells with asset protection, and design it with maintenance. So when I talk about maintenance, that's synonymous with maintenance and rehabilitation here is really what I'm talking about. So the best way to look at well cost is the total life cycle cost. This is something that was popularized by Marvin Glotfelty out there in his McElhaney speech in 2012, I believe he did that. And it's really a good concept, because what Marvin is doing is he's really looking at the total cost over the lifespan of the well. So you're not only looking at your initial well cost, which is what most people tend to focus on, but you're also adding in periodic maintenance, well rehabilitation, repairs, and anything else that gets in there. And we get down to the end of the life of the well, and we really look at what our total cost is over the lifespan of the well. And when it comes down to it, it's really a matter of the rehabilitation, the maintenance can add up over the lifespan of the well. If you're asking it to go 70 years, that can be more expensive than the initial cost of the well itself. And so, uh, so when we talk about rehabilitation, one of the considerations is it's I like to say it's all about the energy. What we're trying to do is true well rehabilitation is going to get outside the well, go through the screens, into the gravel pack, and out into the formation. There's a lot of well rehab contractors that'll get in there and shiny up the inside of the well and make it look all nice, and they never touch what's outside the well. And in order to do that, you're going to have to supply sufficient energy to get, if you're using chemicals, if you're just using surge blocks, you're going to need to apply that. You're going to need to get through the screens, and you're going to need to get out into the gravel pack, and you're going to actually get out into the formation with the chemicals you're using and just surging to clean out your mineral incrustations, your bacteria infestations, and your biomass. So it's really a matter of getting outside, and quite frankly, there's a lot of well rehab contractors out there, or people that say they're well rehab contractors that don't understand this. But if you're designing your well, you really want to make this easy to do. So this is something that's really important to keep in mind, is transference of energy during the well rehabilitation process. So it's all about the energy. So okay, so now let's get into some of our considerations for maintenance and rehabilitation. There's some areas we're going to look at. We're going to look at the casing, the gravel pack, the screens. We talk a little bit about well profiling and just accessibility too. I mean, you need to be able to get in there and do this maintenance. So casing, a lot of times we're looking at stainless steel. We're looking at corrosivity. We're looking at a lot of PVC wells these days, and I'll talk a little bit more about that in a minute. Other types of steel, HSLA and mild steel. We see a lot of mistakes here. I got some, plenty of instances where I see where they put mild steel and stainless steel together without any connectors that are going to protect that, and you enhance corrosion rather. So you're not saving money over the long run. PVC wells are a little bit of a special class. We're seeing a lot more of it because PVC has been a little bit cheaper with supply chain issues these days. Sometimes it's not, but people like the convenience of PVC. Let me just say, I'm not a huge fan of PVC wells, but I can see where they do apply in certain circumstances. The challenge with the PVC is it's a little, when it comes to rehab, you can't get quite as aggressive with it as you can with something like stainless steel. So I kind of look at that, and we've seen things where PVC can be damaged, and so it's yeah. Ned also points out fiberglass. I really have not. I really have not seen a lot of fiberglass wells, so I'd be interested in hearing more about that. I know they exist out there. I just don't run into them that much. So, but it is another option. So it's just something that in my experience, I just don't see it, and really haven't specified it for anything. So thanks for pointing that out, Ned. All right, so really, well, let me back up a little bit here. So when we get down to the composition, things like stainless steel and PVC are a little more resistant to things like mineral incrustations, biofilm formation. They're not totally resistant to them. I've seen plenty of stainless steel wells get biomass, but usually what happens with things like stainless steel especially is you can go longer between well rehabilitation. It just doesn't, and this is a general rule. I mean, we get some areas where we get really bad iron bacteria, and it's almost nothing stops it, and you got to go back in more frequently. So it's a, it's on a case by case basis, but as a general rule, stainless steel is going to stay cleaner for longer, and the intervals between well rehabilitation cycles are going to be a little bit longer. So if you're looking at your total life cycle costs, then using something like stainless steel as opposed to mild steel, not even taking corrosion into account, is probably going to give you a longer cycle and reduce your costs over time because you're going to have to do well rehabilitation less frequently. And with well rehabilitation costing, say, to go in for a typical well, $35,000-$45,000 for a well rehabilitation. If you're spreading out the interval from 3 years to 7 years, you can see over the total life of the well, those costs can really add up. So stainless steel, it's going to be more expensive up front than mild steel, certainly, and HSLA, which I don't really think gives you a lot of benefit, a little bit, but I tend to look at stainless steel as a good investment because usually the additional upfront costs are going to be more than offset by an increased lifespan on the well. So in some cases, you may get 2 or 3 times the lifespan with stainless steel than you would with mild steel, for instance. So PVC, the jury is still out. I think we haven't seen a whole lot of PVC wells lasting 70 years. The problem I've seen with PVC is especially in places like California, they're a little more flexible, so you can lose with the ground shifting and the ground moves in California and in other parts of the country as well, but especially in California. I've seen wells, shifted around and actually breaking the PVC where you don't get that with stainless steel. There are ASTM standards for tensile strength and that you can look at, and I don't have those cited up here, but that's it is for longevity. I'm really kind of a classic guy as far as that goes, and I look at stainless steel. So, and like I say, I don't know much about the fiberglass, but I would assume that probably flexes a lot like the PVC, and that might be good too. I mean, because sometimes we can actually see wells get sheared off by earthquakes, and not a whole lot you can do about that. So, all right. So gravel pack is another area, and normally what we're looking at with the gravel pack is the composition. We want it to be silica grains for the most part, and non-reactive. We want it to be rounded. We want the sphericity to be pretty high. And we want it to be relatively uniform. So these are generally our considerations for gravel pack, but we want to focus here on a couple things. What we want is our gravel pack, in order to optimize for our well rehabilitation, we want our gravel pack to be as spherical as possible and a uniformity coefficient of less than 2.5. So that's pretty tight, pretty uniform, and that is going to give us a pretty efficient well. So I think I got, a uniform spherical gravel pack will minimize head losses at the well and improve well efficiency. It's a more efficient design. So the more spherical the gravel, the more efficient the well. We're really looking at a couple things here. Is improving those head losses, and we want to reduce and the head losses really are a result sometimes of turbulent flow. We want laminar flow into the well. We want a relatively low entrance velocity. Water coming in too fast can also create turbulent flow. So a very uniform spherical gravel pack can minimize those head losses. And this is kind of what we look at. Another consideration also that I didn't mention was that we really want to look at the fact that the sand grains are non-reactive. They're more resistant to the development of mineral incrustation. It can still happen, but happens a little more slowly, and the more efficiently the water can get through there, and the more laminar the flow, the less likelihood, or the slower the process of development of mineral incrustations and biofilm. So this is your typical gravel pack, and we can see this is a nice little sand. You can see probably some feldspar particles in there, but it's mostly a silica sand. Pretty rounded. There are some things that are subangular in there, but this is pretty good. A lot of times we're seeing in California, we're seeing a lot of crushed rock and just not a really good or efficient gravel pack. Some of the best gravel pack comes from Minnesota, and Texas. There's some really nice beach sand types of deposits that they mine, but that's going to be a lot more expensive, and so a lot of people go with more local stuff, and so you get some of this crushed rock. It's just not quite as efficient, and you're going to have some problems over time. And it's something that a lot of people don't. They say, okay, we run our sieve test, we design up our screen sizes and our appropriate gravel pack size, and go out and buy it, and that's what we use. And they're not really considering the composition of the gravel pack. Seems like a tiny detail, but it can make a big difference over time. So something that we're seeing more of these days is the silica beads, and these started off pretty expensive. Price is starting to come down over time, and I'll tell you, for efficiency in the well, the silica beads are really probably the most efficient design. So balancing the cost versus the efficiency and looking at that over time, it can make it worthwhile. So the silicone beads, I know Johnson Screens has some. There's a number of people out there that sell these things, and they are not quite perfect spheres, but about as close as you can possibly get. So this is going to be a lot more efficient gravel pack than you're going to get with even the best natural type sand type gravel pack. So I really look more, if people can afford it and they're well designed, is really going with the silicone beads these days, because it's just going to be, and because they're all silica, they're non-reactive. It's really going to slow down the process of development of mineral incrustations. It's a lot more efficient design. You're going to see cost savings over the lifespan of the well by going with silica beads over a regular sand pack. So this may be a little controversial to some people that say, I just don't want to spend that money. But over a well lifespan of 60, 70 years, just the improved efficiency can make a difference. Another thing we want to look at is gravel pack thickness. So say the AWWA, American Water Works Association A100 standard says 3 to 12 inches is an acceptable gravel pack thickness. Now, my feelings are that, oh man, what is that? So there's two of me, sorry. Get those little glitches when you're live. Okay, so for maintenance purposes, I think you go with the thinnest gravel pack that prevents sanding, and that's going to be the most efficient for rehabilitation. It's a thick gravel pack is going to make rehabilitation a little more challenging. This may be a little controversial here, but and maybe not. But my feeling is, if you can get by with a 3-inch gravel pack, depending on the type of formation, of course, that's going to allow that energy transference that I pointed out earlier when you get to well rehabilitation, and make it a lot easier process to clean the gravel pack out. If you have a 12-inch gravel pack, it's amazing how quickly, when you're using a surge block and even things like jetting, how quickly that energy dissipates once you get outside the screen. And think about it a little bit here. Even if we have wire wrap screens, if you have louvers, you're losing a lot of energy going through the screen. So it's really hard to maintain that energy to get far out in the formation. So just even an inch or two can make a big difference. So my recommendation typically is look at keeping that gravel pack to kind of a minimum, and you probably don't want to go any thinner than 3 inches. That's kind of the minimum that AWWA specifies, and so I'd look at 3 to 4 inches if you can get away with it, and it really depends on the aquifer characteristics. So you're going to need to look at that, and obviously we want to. The primary purpose of the gravel pack is to allow water to get into the well as efficiently as possible while minimizing sanding. So it ends up being a balancing act. But I say keep the gravel pack as thin as possible, and that allows you to keep it cleaned out when you do well rehabilitation. All right, well screens for maintenance. Moving on to screens, we want to have a sufficient open area to reduce entrance velocity and allow for efficient well rehabilitation. And once again, transferring energy through a really small screen, pretty difficult. So it's and more challenging anyway. You may spend a lot longer working on these things. So and it increases your cost of doing well rehabilitation. So open area, obviously, you're going to get maximum open area from a wire wrap screen, but louvers actually do a pretty good job, but there's a big difference in open area between louvers and wire wrap. And as far as efficiency for getting out into the formation, transferring that energy out into the formation, a wire wrap is going to be a lot more efficient. With a louver, you're basically getting a lot of deflection with the louver. It's like a little shutter, and you're pushing that water out. It's gonna hit the louver, and it's going to deflect downward, and so not quite as efficient as wire wrap. So I'm usually, when it comes to a well, I'm kind of a, especially on a municipal well, really stainless steel and wire wrap screens is usually my design consideration, unless there are some other factors in there. But that's really my default position. So we want to have sufficient open area, and open area really means what is your slot size, your screen opening size. So now this is something I look at a lot of wells, and especially PVC wells. It's what's up with that 0.032-inch screen size. It's awful. Other people may have an opinion on this, but I run into a lot of PVC wells that have an 0.32 screen size. Don't do that. And here's why it happens is 0.032 is generally kept in stock a lot by a lot of drillers because it's used a lot for groundwater monitoring wells, where maximizing your production is not the main goal of a groundwater monitoring well. So, but because it's in stock, it tends to get used a lot. And if people aren't paying attention, you end up with wells that have a 0.032 screen size. It is just not efficient, and it really creates challenges for getting that energy out because you're dealing some really fine slots here, and it makes life difficult. Don't do that. It's something it's on the shelf. A lot of drillers have it, and it ends up in a lot of production wells, and we just see it out there, and I just scratch my head all the time. So don't do the 0.32 slot. And let me just show you here. Here's an example of a well that's going to be a little more challenging to rehab. This one we're looking at right now. So if I can get my finger here, so you can see here we go. We got our slot size, 0.32 factory slot here. We also have our borehole diameter, 17.5 inches, and an 8-inch well. So if I get my finger right there. There's a PVC well. So basically, we have a 5-inch, 4.5, 5-inch that's gravel pack thickness. That's kind of borderline on what I would recommend. But you take a little bit thicker gravel pack than what I normally recommend, and you couple that with a 0.032-inch slot, you're going to have a challenge getting energy out into the gravel pack and the formation. So it's just, challenging to do that. And with a PVC well, once again, most of the PVC is Schedule 80. It's going to be fairly durable, but it can still be damaged a lot more easily than metal cased wells. So you're going to have to be a little more careful with this. So it's, once again, it's why did this particular well end up with an 032 slot? And my guess is typically it's what the driller had, and it was easy to get, and the price was down there, and it just kind of, so I typically don't go anything lower than 0.05, 0.06 is for most alluvial type wells. I mean, there's really no reason to do that with an appropriate gravel pack. You're going to be just fine unless you have some really weird circumstances. All right, here's the other problem with those fine slots is well development is going to be a challenge. Well development, we really get on the wells, and you can see, there's a temporary pump in the well, and we're really getting after it. We're cleaning out the drilling mud, reducing the turbidity in the sand, and increasing the specific capacity in the well. So we're really getting after it. If you can't get at things because you have this really fine slot size, then you're going to get incomplete well development, and it's going to haunt you. This is a well in Northern California where they actually drilled this in fractured rock, and they cased it and screened it. This is an 032 slot, and you can see a year after and this was drilled by a major well driller. A year after they had drilled this well and supposedly developed it, you are still getting drilling mud bleeding into the well. Not a good situation because it's plugging the well up, and this well never got to the production that it could have because you got all that drilling mud clogging things up, and obviously over time drilling mud is going to gel. You got some polymers in there, and just the bentonite is going to gel over time. So you don't get the drilling mud out. It's going to gel up, and you're going to have an underproducing well for its life. And we went in and did our best to clean this up a little bit, but it was just too far gone and just really difficult to do this. If you had a larger slot size, then a little easier to develop and rehab over time. So here's just a good example of that, and so stay away from the 032 slot. I just can't recommend it. Some people may think it's okay. I can't recommend it. I don't think it's good for a water well unless you have some very special conditions in a very fine formation, for instance. It's just not good. So there you go. All right. So this probably is going to be a little more controversial because I know it goes against some people, but most wells used to have like a sump or basement, like I call it, an area, an open area well below the pump intake, and supposedly this was for storing water. Well, you start pumping on a well, and you're, for one thing, the pump is not going to be able to get down very deep below the pump intake, so you're really pulling water mostly above the pump, and it's not moving the water down there. So because the water isn't moving down there, conditions would go anaerobic, we would see the bacteria in the well would die. You get organic mass accumulating at the bottom of the well. It would go anaerobic. That's anaerobic bacteria are your bad actors. You get sulfur-reducing bacteria. A lot of pathogenic bacteria are going to be anaerobic, and also things like coliform or facultative bacteria, which means they can be in aerobic or anaerobic conditions. Anaerobic, to back up a little bit, basically is lack of oxygen. So you don't have any oxygen down there because you're not getting any water flow in the well. So, but facultative bacteria can live in both anaerobic and aerobic conditions. So that's a situation where coliform can get in the bottom of your well if you have a long sump and breed, and now the bacteria will migrate through the rest of the well, and you basically have party time for the bacteria in the lower part of that well in these sumps. So our design has really gotten away from doing these long sumps to the point where we're just having no sumps at all, and just screening right to the bottom of the well, so you can take advantage of that and really reduce that zone for anaerobic conditions to develop and the bacteria thriving in there. Now, what I'm going to say is probably a little controversial because I'm going to go against that a little bit. I think you need a small sump, no more than 5 feet, sometimes 2 or 3 feet at the bottom of the well to allow access for rehabilitation tools. I have run into a lot of situations where we've seen wells screened completely to the bottom, and because we're using things like a swab or a brush that need to go up and down, we can't get a full stroke at the bottom of the well and clean out that lower section of the screen. So in effect, what you're doing is that is plugging up, and you're not able to effectively clean it, and you're creating a sump basically from your screen zone because it's going to plug up, and then you're going to get your anaerobic zone developing in there too. So compromising by putting a small sump of just a few feet so you can get a full stroke on the swab and the brush, so you can clean that very bottom of the screen, I think is a good design consideration, and usually what I look at. You don't want to go any more than 5 feet. People like to keep 5 feet. I like 2 or 3 feet. Sometimes people don't like cutting things down that much. You gotta cut it and to get 2 or 3 feet. So sometimes people like to go 5 feet. I like to go smaller than that, just enough so you can get that full stroke on the well rehabilitation tools and allow access to the very bottom of the screen to clean it, to keep the water flowing, and that's going to maximize your well flow and really reduce that population of the bad actor bacteria that's going to be accumulating at the bottom of your well where you have stagnant and anaerobic zones. So controversial. Yeah, Ned says proper material selection for the sump along with proper pump configuration and placement go hand in hand. So yes, absolutely. You want to have the pump right down there, so you don't want to have a whole lot of space below the pump. You want to have that intake down there and maybe a small sump below that, and that's really going to reduce those conditions at the bottom of the well where you can develop the anaerobic zones. So just an example of that. Here's a well, and this is kind of a funky, this was kind of an as-built. I kind of came in later, but you can see here they screened all the way to the bottom of the well. I got some well videos of this one. We designed a well rehab. They went down there and really they were not able to and the video proved this. They were not able to get all the way to the bottom of the well to fully rehab this. So they're going to have some problems a little bit later with the very bottom of the well. And it's just one of those things that they did not design this well to properly take advantage of well rehabilitation. There's another mistake on this well too is they have a mild steel casing directly coupled to a stainless steel screen sections, and so without benefit of a dielectric coupler, and so you have problems with that also. So a number of design mistakes here, but certainly not designed for well rehab. They had an 065 slot on this one, so it's probably pretty good. 16-inch diameter wire wrap 065 slot. So I know these drillers; they do a pretty good job. It's just that there was and I don't know if there was an engineer that designed this up or whatever, but a few mistakes on this design here. So it's not maximized for longevity or getting the rehab done. So. I talked a few weeks ago about well profiling and zone testing, and so I'm not going to hit that really hard here, but basically we're talking about designing wells to avoid contaminants, and really what we're doing is database techniques to balance flow versus contaminant concentrations. So really a well profiling procedure looks something like this: is we go in, we thin the mud, install a temporary screen if necessary. We conduct ambient testing, and that's going to be under non-pumping conditions. So we're going to go in with an electromagnetic flow meter or some kind of dye trace method. There's heat pulse flow meters, spinner flow meters. There's a number of different flow meter techniques out there. I tend to prefer the electromagnetic. The dye tracing is we've used that in the past, and that's worked pretty well also. And then we'll go in and we'll install a test pump, and we'll do dynamic testing. So that's testing under pumping conditions, and we really compare the two. Then we'll go in and we'll collect depth discrete water quality samples. If we have, say, nitrates, if we have arsenic, and then we'll analyze the data and design the well accordingly. We'll do a mass balance, and we'll really look at designing the well so that we are designing that well to maximize flow while minimizing contaminants coming into the well. This is a design phase decision, I think. You can go back and do this and modify a well later. It gets a little more expensive if you're doing it up front. I always recommend well profiling, and actually there's a lot of fans out there of traditional zone testing, which I find slow, laborious, a lot more expensive. Well profiling will give you a lot more data and a lot more granularity to make these decisions on how to design your well. So I usually spec out doing well profiling as part of my. You're going to do it about the same time you're doing your e-logs, and you're just going to go in and follow the e-log and do this at the same time. It just really helps with your well design. So. Here's just an example, USGS example, where they went in and you can see the e-log data. They ran SP and lateral resistivity on the left there. And then you're looking at borehole flow. You're looking at, in this particular case, they're looking at arsenic concentrations. And then you got the well lithology on all the way over on the right. So we can see that we have higher arsenic values down in the lower part of the well. We have our flow data is showing us that we have less flow at the bottom of the well than we do in the upper part of the well. So in this case, we probably wouldn't reduce production that much by going in and sealing off the bottom part of that well, getting rid of our arsenic, and then just taking the cleaner water above and really minimizing our treatment. Sometimes you can actually eliminate the need for treatment doing this technique. So I did a lot more. I did a show a couple weeks ago zone testing versus well profiling, you can go back and look at that. That's on the Groundwater Guy YouTube channel, so you can check that out if you're interested in a lot more detail. I dive into it in more detail, and we teach some classes on this too. But it is something that I think should be done, especially if you suspect you have water quality issues. Getting your seals right in the case of nitrates is usually a shallow groundwater surface water issue. So it's where do we place our seals? The profiling can help with that. Arsenic is going to tend to be something like it's usually going to be related to a specific geologic horizon in the well. And if we can identify that and seal that off, then you got a good possibility of reducing the need for treatment in the well. So well profiling is something I pretty much always specify on new wells that I do, and it's just paid off in spades. Even high TDS water, we've seen specific zones in wells where you get TDS maybe running over 1,000. You don't want to take that water unless you can sufficiently dilute it down. And but you're raising your TDS levels in the well, and that can create all kinds of problems for you. So just stuff like that, we can map out with the well profiling in great detail and design the well around that. So it's a great tool in our toolbox. And once again, if you have zones that say have high TDS, now you're looking at the potential for mineral incrustations to develop, and that's going to be a long-term maintenance issue as well. So keep that out of your well if at all possible. If you don't have to sacrifice a lot of your well production in order to do that, and well profiling is one way to do that. And lastly, this is a thing that's kind of a little more hard to specify, but accessibility. I see a lot of situations where it's kind of like, okay, we put in a well in an urban area and it's very tight, and there really is no room to come in there and do maintenance without standing on your head and making a lot of compromises to do that. So it's something that we really want to look at is how the heck do you get in there? I mean, are there power lines that we need to worry about if we got a mast up on a pump rig? Sometimes the power lines will come in later, and so it's something we need to look at is accessibility to take care of our wells and do the maintenance and rehabilitation. If you're doing well rehab, you're going to have supporting equipment. You're going to have other vehicles out there. You're going to have tanks and stuff to mix your solutions and to neutralize it. You're going to want to have access to some pump to waste facilities after you neutralize your solution. What do you do with that? So these are all things with accessibility, and it needs to kind of be designed into things. Here's just an example of a decent well design. This is a well enclosure, a little house, a brick house surrounding the well to protect it from the weather. They got chlorinator and some gauges and stuff in here that need to be treated. So, but you can see here they have roof access, so you can get in there with a pump rig or a rehabilitation rig. You just pop that lid off, and you're able to access the well and get in there and do that. I've seen them where they have removable roofs that are a little more challenging. This is a little easier to get on and off, as opposed to something like this where they got their well inside here, but there's really no provision to and this well is having some work done on it, and how do you get in there? Basically, they have to mostly take down this building and destroy the building and rebuild it in order to get access to this well to do. We're doing some well modifications here, and that is something that they're going to basically just have to take down this building and rebuild it. So not really thinking about the long term here. So and there's other issues as well with accessibility, but this just gives you some thoughts here as well on that. So the bottom line is low bid does not equal the lowest cost over its lifespan, and that's something that a lot of people can't get. They're out there. getting bids on wells and getting bids is all well and good if you develop the specifications that are more than the minimum, and that's what you bid on. So you really got to want to look at developing specifications that you send out for bid that take well rehabilitation and well maintenance and even things like access for repairs into consideration. And some of the things that I suggested here are important. You may have some other ones. Some people, camera tubes in new wells. Some people love them, some people hate them, but that's another thing as well that people don't think about is how do we get access to video our well without pulling the pump every time. So that's another. It's related to maintenance as well. So lowest bid does not, and I say it does not equal, it does not necessarily equal the lowest cost over its lifespan. So we really need to look at the fact that the most expensive well up front could actually be your cheapest well over when you look at the life cycle cost. Maintenance and rehabilitation are important cost components over the well's lifespan, and those can actually add up to more than the cost of the initial well installation and construction. So it's really an important consideration. You really got to factor this in. If we have a well that we're designing for 60 or 70 years, what kind of intervals are we going to look at maintenance and rehabilitation, factor those costs in, and then look at your upfront costs. You add all that together and basically take some if you really want to get fancy, you can take inflation factors and discounted cash flow factors and really get, do your total financial analysis. But that's really what we're looking at is the cost of that well over its life. And that's going to be important. You may not be there when the well gets down to the end of its life, but you're going to hand it over to somebody else who may hand it over to somebody else, and they're going to be pretty appreciative that the well was designed so that it could take into account maintenance and rehabilitation, and that in the long run we're going to optimize the performance of that well over its entire lifespan. So so designing a well with maintenance in mind can reduce your total life cycle costs, and that's the bottom line here is these are some considerations. You may have some other ones. Pop them into the comments if you got, or go back later and comment on the video. I'd like to hear what your design considerations are for these things. But like I say, I get out there and I basically see situations where people just haven't designed wells with any of these considerations in mind, and they say the run to failure or just run it till it quits model is still probably the most at least for small water districts, the most common one out there, and that is true. But if we're going to ask a lot from our wells, we really need to make it easy to go in and fix that up. So if you had a car out there and you didn't have an oil plug on it, so you could change the oil and you had to take the engine apart every time, that would not be very, very efficient design. So you can translate that to well design for rehabilitation and maintenance. So that's we want to make it easy to do, and it's going to reduce your costs over the lifespan of the well. So that's it for today's show. I got some things I wanted to point out. I got some classes coming up here. This is a 1-hour class on June 8th for the well health check on diagnosing problems with your well, and this is going to be the first step before you can do well rehabilitation. So these are paid classes, so that's coming up. That's going to be a 1-hour class, so we usually get good reviews. I pack a lot into that 1 hour. If you want a little bit more detail, coming up on July 12th through 14th, systematic well management. This is really optimizing performance at every stage of a well's life. So, hey, Ned, thanks for that. Yeah, we're definitely going to have to talk. So Ned is really an expert out there. I really respect his opinion. So there you go. Thanks, Ned. Um, while I'm doing my sales pitch here. So this is going to be July 12th through 14th. We're going to do it for 2 hours a day for 3 days in a row. That works well for operators' schedules for water systems. So that seems to work well. Another paid class. So we dive in a little deeper on this because it's 6 contact hours. Both these classes you'll get certificates for the training. So if you need contact hours, there you go. So this is wrapping things up. We stream into the Groundwater Guy YouTube channel and also on LinkedIn. Those are the two places I go. Seems like that's where I get my most traction. I've tried streaming onto Facebook. Don't get much traction there, so this is where I go. But if you have someplace else you'd like to see me, let me know, and I'll do that. But all my older videos that I've shot, and we do this every week, are on the Groundwater Guy YouTube channel on YouTube. So check them out. We got a lot of interesting stuff there that you might be interested in, and you can get a hold of me on LinkedIn. I put my email address up there earlier, but you can get a hold of me on LinkedIn also. If you want to be a guest on Groundwater Talk Live, if you got stuff of interest to the water industry, then let me know. This is the link to do that. You can schedule a time, and I'd love to have you on. And so I like to have guests on every now and then, so people don't just have listen to me rattle on and do that. So, all right. Thanks for watching. Don't forget to subscribe to the YouTube channel. Hit the little bell so you know when we have new video up. That is the Groundwater Guy YouTube channel, and we will see